Hello, we are Team 961 for Hyperion. Today we would like to share with you how Pure Pursuit works, what it is, and how you can use it in your own autonomous. This is a great example of our autonomous program using Pure Pursuit in the center stage season at the Maryland Tech Invitational, a prestigious competition for 40 of the top robots in the world. Our robot is the yellow and black one driving closer to the camera. The motion of the robot is smooth, so it does not waste any time. This is also the world record autonomous score in an official match, with all 4 preloads and 12 white pixels scored. Note that the match record misscored the parking bonus. So what is Pure Pursuit? It's a path following algorithm, such as Roadrunner, that basically takes your current robot's position plus the path you want it to follow and converts that into movement vectors that the robot should follow. There are a few other different path following algorithms that are commonly used, the most common being Roadrunner, and also PID to point, and finally Pure Pursuit. There also exist many various custom implementations that are less commonly used. Some advantages of Pure Pursuit include that it is very robust, because it calculates its movement live during each cycle while the robot is moving. It means that if the robot strays from its original path, it can correct for it immediately. This is as opposed to some other path following algorithms that calculate the path or calculate the powers before the robot moves. Pure Pursuit is also fast because it uses the maximum possible velocity the robot can go at by setting the motor powers at 1, and it also tends to move in the forward direction, which for Mecanum wheels is faster than strafing. Finally, it is very educational, and we learned a lot through making our own Pure Pursuit program. However, Pure Pursuit also comes with some downsides. It is quite difficult to use because there are no optimal existing libraries. You'll have to figure out how to make your own Pure Pursuit based on a base of the actual geometry. But then you'll have to write a lot of custom code to make the Pure Pursuit run well and be easy to use. Also, because it calculates its motor powers live, it can be unpredictable sometimes, so it'll move slightly differently. So how does Pure Pursuit work? First, you draw a circle around the robot's current position. Then you have the paths that you pre-tuned and for your autonomous that you want the robot to follow. These can usually be lines, or it can also be different curves depending on your needs. Then you find the intersection between the circle and the path, which is called the follow point. And finally, you make the robot drive towards that follow point every loop, which means that the follow point will gradually move along the path, and the robot will always keep following that follow point. So to make your own Pure Pursuit implementation, here's some good resources. So first, you should watch Gluten Free's video series, which is titled FTC Programming Pure Pursuit Tutorial. This includes a lot of the base structure of the Pure Pursuit, and some of the code can be directly copied, but of course there's going to be a lot of custom adjustments that you'll have to make, and the base code may contain errors that you might need to fix. In addition, this video series gives you a good intuition of how the Pure Pursuit works and also gives a few ideas for how you can improve it. In order for you to know where the robot is on the field, you'll need a localizer. So basically, a localizer takes your geometry inputs and converts them into robot coordinates based on where you started the robot. It's recommended to use a pre-made localizer because the math is pretty complicated, and all the math for a custom localizer would pretty much be the same anyway. So you should plug in the localizer coordinates, which it spits out directly into the Pure Pursuit as your current robot position. Pure Pursuit only outputs movement vectors, which means that it effectively only gives you a single arrow of which direction the robot should move relative to itself. However, the robot needs to drive using wheels, so you'll need to convert the the single movement vector into each of the four wheels' powers. This can be done using a simple mechanism drivetrain code, which basically converts the movement vector, which is usually represented as a joystick input, into wheel powers. So here's some common problems that you might see while making your own Pure Pursuit program. First is that the robot doesn't move in the correct direction. This is often a result of incorrect coordinate system conversions, especially between the localizer and the Pure Pursuit program. So definitely check that. Furthermore, X and Y directions, or forward and strafe directions, may also be incorrect and need to be correctly identified to be able to run the program. Finally, some of the geometry might be incorrect, so definitely check through all of it and debug it and make sure that the follow point is being calculated correctly, as well as the wheel powers. Another common problem is that the robot gets stuck and oscillates. This is because when the robot is somewhere in the middle of the path, it will often have two intersections with the path. So therefore, the robot chooses the incorrect intersection to follow. So you'll need to figure out which intersection is the correct one and follow that one only. Another problem is that the robot overshoots excessively. To fix this, you'll have to increase the follow radius, which smooths the path more aggressively, which means that around sharp corners, the robot will take a smoother path. One more problem is that the robot does not follow the path well enough. To fix this, decrease the follow radius so that the robot follows the path more closely. If you don't, the robot will cut a lot of corners, will probably hit a lot of obstacles.
Alright, now let's take a look at some features we can add to aid development with this algorithm and extend its functionality. A dynamic follow radius helps a lot to solve the last two problems. At high speed, it's better for the path to be smoother because fine corrections can't be applied as well. Whereas at slow speeds, it's often intended for the robot to follow the given path more precisely. By defining the follow radius as a function of speed, we can meet those two requirements. We found that a lot of time during our tuning process was spent on waiting for our code to compile and launch on the robot controller. By loading our paths in from files during initialization instead of hard coding them, we're able to make changes much faster.
Creating a path editor helps make edits and tweaks easier. Instead of guesstimating coordinates, you can see the whole path on the field at once. The editor reads your path configurations and plots them on an image of the field. You can also implement Pure Pursuit in the path editor to estimate what path the robot will actually take on the field. When the robot is following curved paths, it tends to overshoot due to the momentum the robot has. Tweaking the motor powers to move further inwards on the curve allows the robot to follow paths more nicely. Wolfpack Machina's movement breakdown video from the Power Play season explains this in further detail. You can add backup paths for recovering from mistakes. If the robot gets stuck on terrain, a safety reset path can help the robot back up to a safe position before resuming the previous path. Although preventing terrain collisions entirely would be ideal, this handles the rare cases where something goes wrong and allows achieving a higher autonomous score than without backup paths.
Thank you for listening to our presentation.